All right, hello everyone. Thank you for coming. So introduce myself real quick. My name is Garrett Foster. I am a researcher over on the team at SpectreOps. Been there for a little over 2 years now. Background in red teaming, pen testing. Spent a little bit of time working in a SOC, doing kind of like security analyst work, and then got my introduction into IT, working as a help desk and all the way up to sysadmin. Some of my responsibilities over at Spectre, I focus on endpoint management software, and then as a researcher, my responsibilities are try to do some red team enablement and to find new attack paths to try to implement into the Bloodhound graph. Okay, so let's get into it. So this slide is an LDAP filter, and if you were to run this filter, it will show you every single clustered resource in a domain. And my goal for this presentation is that you'll be glad you took a photo of this, because by the end of it, you'll want to search for these whether you're on the red or the blue side. So on the agenda side of things, how am I going to convince you that that was a good idea? Break it out into 4 sections. We'll have an intro, kind of get everyone on a baseline of what we're going to be talking about, what clusters are, and where they came from with Microsoft. We'll get into story time. I'll talk about how I even got onto clusters, like what even led to all of this, and then do a bit of research together. And we'll cover some attacks. So if we were to compromise a cluster, what could we do with that kind of control, and then how bad could we actually make the fallout? And then at the end, we'll give I'll give you some defensive advice for remediation, detection, and so on. So, okay, so let's get into it. Failover clusters. To kind of answer this question, we're going to go back in time a bit, all the way back to 1997. And I know some of you in this room weren't even born yet. But in the spring of '97, Microsoft was holding an event. It was called Scalability Day. They were hyping up the release of Windows NT 4.0 Enterprise Edition, and a feature in that release was Microsoft's cluster server. So this is Microsoft's first introduction into high availability. I think it's pretty interesting that this blurb talks about how if one of your servers were to go down, the next one would pick it up, because your one server would lead to the company falling over. So high stakes back then. But I bring that up because this is the current definition that Microsoft uses to define what Windows Server Failover Clustering is. So it's a set of independent computers that work together to increase the availability of applications and services. So in 30 years, overall, the goal with the service hasn't changed since then. So which applications and services? The most common that we'll see today are file servers, and easily the most common are databases. So these two applications and services represent single points of failure. So if the file server or the database server were to go offline, lose access, whatever happens, you lose access to those resources. So to kind of fix that, we have clusters. We'll have multiple servers to be able to support that one resource. So if we lose access to one, then the next man up kind of picks up control of that. OK. So story time. Every week at work, we have kind of a meeting where the services team will get together. We'll talk about what we're working on and have kind of a team highlight. And at in this particular meeting, we had a couple operators say, they were pursuing this attack path. It was successful, but they saw some really weird behavior. So let's kind of walk through what they had seen. They had just run the Bloodhound collector, so now they've got it up in the graph, and they're trying to follow this attack path. So let's kind of break down what they were looking at. On the left side of the graph, we have this relationship between the domain computer security group and a machine account. So they had control of a machine, so they had an identity that was a member of domain computers, and had this edge, write account restrictions. So write account restrictions is relatively new. In the last few years, it was discovered by Dirkjan. And in his blog, he was investigating what happens when you stage computer objects. So if you were to create one, the default setting is that the permissions for who can join that machine to the domain is set to domain admins. But he was investigating what happens if you delegate that permission to a different identity. And what he found is it applies this property set called write account restrictions, and included in that property set is the permission to configure resource-based constrained delegation, or RBCD. If you are unfamiliar with RBCD, a few years ago, my boss's boss, Alad Shamir, posted this blog called Wagging the Dog, Abusing RBCD. It says it's a 41-minute read. I'm still reading it today, so take that for what you will. But the relevant piece of the blog that's going to apply for what we're looking into is that you can abuse RBCD to hopefully compromise that host system. So this is what the operators were looking at. They said, okay, cool, let's abuse write account restrictions. We'll set RBCD and then compromise that computer. Because on the other side of that graph is we had a logon session for a tier 0 user. So they're thinking, let's pop the host and we'll just steal the credential material for this user and that'll get us towards our objectives. So that's what they did. It was a non-invasive test, so like off-the-shelf tooling was fine. They pulled up some scripts from Impacket and set RBCD and tried to impersonate an admin role and then pop that system. Only problem is they were getting errors. So Impacket, if you've ever used it, errors are kind of a normal thing. But the errors in this case, we were seeing something unusual. We're getting bad network names and kind of like host name resolution problems, which they were certain DNS was working, and then they try to use other tools from the tool set, so WMI, exec SMB, whatever it may be, all of them were failing. So they pivoted, they switched to, let's take that RBCD ticket that we've generated, where we're impersonating that admin, we'll just take it to a Windows system, and then we'll use it with scheduled tasks. So they brought it over, passed the ticket, launched the snap-in for scheduled tasks, thinking just, we'll launch that and then execute a payload there. And it worked. They were able to create the task, execute it remotely by proxying it, and they got their callback. So cool, we're on the road, let's go grab that credential. The only problem is when they took a closer look, they found that the system that they were trying to interact with, which is cluster.ludus.domain, came back, the payload executed on a completely different host, which is weird. So, but they kind of kept digging, and once they had that access to the system, they were targeting a certain logon user. And after a closer look, they found that the account was there too. So we're on a completely different host, potentially, where the logon session exists. So we're all kind of brainstorming ideas on what this could have been. It's not uncommon to see these DA accounts or these privileged accounts kind of living everywhere. So that was a potential explanation for the account. But the host names, those were causing issues. So some theories were, well, maybe it's like a DNS alias that we're registering. But to set a DNS alias or a CNAME, you actually have to set the service principal names for that alias. So they took a look at the SPNs, and we didn't see any CNAMEs, but what they did find were failover cluster related SPNs. So that's how we got here. So it left me and several others with a number of questions. So why did scheduled tasks work when Impacket scripts failed? So what was going on that's different there? Why that host? Is there any way we can predict it or control the scenario if we're going to execute a payload again? And then what's going on with session data? Is it just that that account is being used everywhere, or is it something else? Like, is something else that we can determine? And then lastly, how does Kerberos authentication work? And no, not in general. I don't think anyone can answer that question, but mainly along the lines of clusters. Like, is there something different or unusual going on with how Kerberos works, which we'll get into. So my usual flow of trying to get the answers to these types of questions is to just lab it out, put myself back in the shoes of the admin role, and to deploy that service and see if I can just quickly get answers that way. So we'll follow Daniel's advice, get a lab set up together. We'll try to get it as properly as we can. So let's do it together. We're going to do a 3-node cluster. I've taken the liberty of getting some prerequisites done already. The feature's been installed on every system, and I've got the storage set up. Those weren't really relevant to the conversation, so I just kind of skipped over that. So we'll start from one node. Actually, deploying the cluster uses an MMC snap-in, so it's called the Failover Cluster Manager. We'll pop that open and start creating the cluster. So it's typically integrated with AD, so we'll find the 3 nodes that we're going to actually use to set this cluster up, just add those there, and then we're going to create what's called an access point for administering the cluster. So here we're going to actually give the cluster a name, and then we're going to reserve an IP address for that cluster name. So we're starting to get a little bit of breadcrumbs about what might be going on. And that's it for the cluster. It's very simple, it's very easy. If all the prerequisites check, everything passes, we'll have a cluster now installed. So the next step is to create the role. So I mentioned earlier that we had the file servers and then the databases are the most common. Database, I didn't want to deal with messing that up, creating that, so we'll just do a file server. It's the easiest to lab out. So we're, again, going to create an access point. This one is called a client access point, and we'll give that a name, and then we're going to reserve an IP address for that name. We'll need some storage because we're actually hosting a file share, and that's it. So now we have a working cluster and role. So what did that do? If we take a closer look at the manager now, you'll see that we are connected to a cluster.ludus.domain namespace. Our roles, so we created the file server role. It's showing healthy, up and running. And all of our nodes, all of our servers have now been promoted to member nodes of the cluster. And now we have what's called a cluster network. And things kind of get interesting here. So on every node, after we set up this service, it's going to have what's called a network fault tolerant virtual adapter. So it's a lot like when you create a VM, you'll see that virtual adapter being installed. But this is how all the cluster nodes communicate with each other. They'll use this network adapter. So there's just a few ports that are required to be open. So the firewall would have to be opened up between all the nodes. The first we'll dig into is 3343 on UDP. And this is where the nodes actually communicate their health. So every second, a node is firing off a packet. It's about 50 to 70 bytes large, and it's in sequential order. So 1, 2, 3, 4, ping, pong. So what it's doing is it's actually a TCP packet that's going to get plumbed through the NetFT adapter, that network fault tolerant adapter, come back, get UDP wrapped, and then it will egress the host through the physical NIC. So essentially every second, so it's sending that out to every other node, and that's intended to have that failover, that heartbeat. So if we lose, I think it's on Server 2019, if you have if you have 20 pings without a Pong response, that's determined that the node is no longer healthy and can't be a part of the cluster anymore. So that's how the heartbeats work. So the other side of the equation is we have RPC. So we'll have the static 135 port, and then we have the dynamic ports for endpoint mapping. And we can see what RPC is used for by just doing a quick Wireshark capture and inspecting the traffic. So this is just a capture of when I was connecting to the cluster using that snap-in that we had seen. It kind of breaks down into 3 parts. We'll see that initial bind to 135, and we see the EPM, or the map request for the cluster API. So the snap-in is providing RPC the actual interface ID for the cluster API, and it's responding, hey, you need to go to this port. So we'll just come back and connect to 55602, which is where the interface is listening, and we'll reestablish that bind, and if we're authorized, you'll see us jump into those cluster API calls and actually interacting with the administrated namespace of the cluster. Which answers one of our first questions, like why did scheduled tasks work? It's not a interesting answer. It's just simply that the snap-ins work and are able to resolve the string bindings and resolve those host names. The in-packet scripts, when you try to execute them, most of them are writing files to disk, so they're trying to capture the contents of those files and they're resolving the host name that we're binding to, that virtual namespace, and it can't find the file path. It just doesn't exist. So fixing that in the in-packet scripts or just running with silent commands and not expecting output, all of them will work fine, which you'll see in a demo in a bit. So let's bring it back to some of the stuff we were building out in the lab, some of the logical components that we'll have to dig into. And those are the VCO, the CNO, and then the node. So the VCO is a virtual cluster object, and it's the computer account that represents the service itself. So in this case, it's the computer object of the file share. So what we didn't see what was happening behind the scenes when we set up the lab is when we create those objects, it's actually creating an Active Directory machine account that represents this service. So it has a machine account ID and AD. So conversely, with the cluster, when we set that up as well, it's creating what's called a cluster name object, and that's the computer account for the cluster itself. So the way these work is that each node in the cluster is considered a member server, and that can own or host the VCO or CNO resource at any given time. It can only be owned by one node at a time, so you can't have multiple VCOs, and and you'll see there's not a lot of nuance to where they're going to be hosted. So each of these represents a namespace, right? So we talk about those access points. So the VCO, when we're connecting to that, we'll have the clients connect to the VCO namespace. This is the users and computers that need to interact with that file share, so they'll connect there. The opposite side is the CNO represents the administrative namespace. So when admins need to come in, troubleshoot the cluster, add more nodes, whatever it may be, they're going to connect to this namespace. So let's visualize it from the lab that we just set up. So we have our 3 nodes, and then since we stood it up on that first node, it's the owner of both the VCO and the CNO resource right now. So that's the status of our cluster. If we were to lose node 1 and it failed, the VCO and CNO will move to the next healthy node. So there's not a lot of control here. Admins can say, hey, I want this to be the primary failover node, but the point of this is that at any given time, any node can own these resources, which gives us some more answers. So why that host? It's just a coincidence. When they connected to that virtual host name, the node that responded was just the owner at that given time. 15 minutes later, it could have been a different one because there's some type of lag in the network. For the session, what was going on there is that Bloodhound, when it runs the session collection, it's using the net sessioning API, which is also RPC. So it's taking a DNS entry for that virtual name, actually running the net session enum API, and the host, the underlying node, the owner node, is responding with session data. So it's actually accurate. It's just we have multiple host names for one resource. Which leaves us with Kerberos. So let's walk through the Kerberos handshake to show you exactly where like my brain broke. So the client, we're authenticating to the domain. We're going to come to the KDC, give us the secret. We're going to have that authentication say, cool, here's my password. I need a ticket granting ticket so that I can access resources on the environment. DC responds, I have my TGT. So now I need to go to the database. I have to come back to the KDC and say, here's my ticket. I've already authenticated. I need to access the database service. Can you respond with a service ticket, and I can take it to the database? DC is like, cool, here's your ticket. I'm encrypting it with the secret of the service that you're trying to go to, or that account's password. I don't care. All I need is a ticket to be able to supply it to the service so that it can decrypt it and authorize me. So I have my ticket. I'm going to come to the database, and then it's going to decrypt that for me and say, cool, you're authorized. But this is where everything broke for me, is the whole point of that shared secret is that I have no knowledge of it. I can't decrypt the ticket. I can't manipulate it. But in the attack path we shared, we're taking a service ticket for one host, and a whole other host is decrypting it and is able to validate and authorize me. Shouldn't be a thing. So I did what any sane person would do, and it was assume the worst. So my first theory was that potentially, okay, every single node or every single identity is sharing a password. Then it was, okay, maybe it's unconstrained delegation or something that I'm not aware of, or some type of impersonation with the cluster service. And this kind of spiraling just continued when I looked at the node that we just stood up. So here's the first node. And now that we're more aware of what's identities are part of the cluster, things start to kind of stand out. So we have the node that we're on, which is the test cluster 2. And then we see the VCO and the CNO resource have active logon sessions. So it makes sense. They're the owner of those namespaces at that time. So if clients are connecting to it, they need to be able to decrypt those service tickets. The only problem is if you check the other two nodes at the same time, we have the same type of event happening. So we have the node has a logon session, and the VCO and CNO have logons on every single node at all times. So it was easy to kind of debunk the spiraling theories, dump the DIT, looked at all the passwords, they're all different. There wasn't any type of delegation going on or anything like that. So the only thing that made sense is that, okay, each node has access to these resources or these identities passwords. So I Googled around a bit, and without knowing what you're specifically looking for, it's kind of hard to find answers. But I found this blog by John Marlin. He used to work at Microsoft for about 2 decades. He was an engineer on the clustering team. And he talks about this repair Active Directory object, so this recovery action. So if you've ever done sysadmin work, this might sound familiar. So essentially what this is doing is it's rotating the password for the computer object in Active Directory. Excuse me. So the idea with this is that you may have run into where a client has lost trust with the domain, and it needs to have that fixed. What's happening there is that the password that the client has, because machine accounts are responsible for resetting their own passwords, it's rotated it, but the domain, the DC, doesn't have the new password. So now we have a broken trust. So this is where my thinking is like, this must be what they're talking about. So here's where things get interesting. We see if this password is different from what's stored in the cluster database, like what's that, we'll have things that cause Kerberos errors. So the cluster database is a registry, a series of registry entries that essentially, that store all of the entries and settings for your cluster. So if you're setting up a network, the IP address, the namespaces, all of those things live in this database. This database is also present on every single node. So my thinking here is like, if there is a credential somewhere, it's likely stored in here. Its only problem is where. So how can we find that? And then the blog finishes up with, okay, so if we have that problem happen, we can repair that. And I'm thinking, okay, let's watch this and see what happens if we were to run this repair function, because my theory here is that, okay, this must be rotating the password. So let's walk through it together. We'll have Procmon listening in the background to just try to capture all the events that are happening when we reset that. And there's a ton of registry activity. If you've ever done Procmon, you've probably seen how chaotic and overwhelming it can be. But I've taken out the key pieces that are relevant to what we're looking for. So the first is this call to the crypto container GUID. So we're querying the value of that, and it's pointing to another GUID. So we kind of follow along where we're going with that, and we'll see another query to this crypto checkpoint, or cryptography checkpoint. And this is pointing to a crypto container, a CSP container, that contains the private key of this certificate pair. And then the data entry is just the hex-encoded public key of that certificate. So OK, cool. We're on the right track. I'm thinking cryptography passwords make sense. So let's press on. And the last event that we follow from that rotate is we see a reg set value to resource data. And the contents of that is this massive encoded blob that looks like it's potentially encrypted. Wasn't DP API, so I needed to. So now my thinking is, all right, I'm going to have to reverse engineer this thing. I'll give it my best effort. So popped it into Ghidra, was having a pretty rough time with things, so I kind of called in backup and reached out to a coworker. His name is Evan McBroom. If you've never met him, he's the author of the LSA Whisperer project. Super smart guy, really, really strong with Windows internals and low-level programming, and is really strong with Windows authentication protocols. So I figured this is probably the person to talk to. Said, hey, I gave it a shot. He says, just send me the binaries. I get on Slack, say, here's the entire directory. The cluster service is the primary service. So he's like, cool, I got you. I'll take a look at this tonight. I try to save face a little bit, say, hey, man, I gave it my best effort. I think I can see kind of how things are going. I just couldn't quite get it to the finish line. And Evan just gives me a thumbs up reaction. If you've ever met Evan, that's a good sign that something good's gonna happen. So 4 hours later, Evan comes back, and he has a solution to my problem. He found that the decryption is done in this specific library, so it's a dependency of the cluster service itself, and it's handled in this decrypt class. And he knows this because Evan is a resourceful guy and had access to the private symbols for that library. And he sent me a screenshot of what he's looking for. Some of you might recognize the red arrow from Evan. But he's pointing to this decrypt class, and that made it easier for him to take that PDB or those private symbols to Ghidra and start doing kind of like the decompilate, to start reverse engineering the binaries. So he throws it in Ghidra. He's like, OK, cool. It turns out there's all these debug statements. So now we have the entire structure of that resource data blob, and we can kind of determine what's relevant to the decryption flow. So we have a roadmap at this point. So he comes back the very next day and gives me a link to a gist. So I'm like, no way, he didn't get this done already. So if you take a look at the gist, he's got kind of like the proof of concept code at the top there kind of shows the structure of that data blob, the resource blob. And if we go down to where we're actually going to handle the decryption, it's probably going to look familiar to some. It's your relatively routine CSP decryption. So we'll get a handle on that private cert, or that private key, kind of what we're seeing with that registry query. And then we're going to decrypt the embedded secret that's included in that blob, use that secret to derive the encryption key for the blob, and then we'll have the ciphertext. We'll decrypt it and have the plain text of that output, or the decrypted ciphertext. So it took us a bit to understand the format that was the result of this decryption, because it was much larger than what we would expect a machine account password to be. And what we found was that it is actually storing the current password for the CNO and the VCO as well as the previous. And this is by design and intended. So this is all about high availability. So if it was 11 a.m. on a Wednesday, people are using these resources, and the password rotates, we would session stomp or ticket stomp all of those connections. They'd have to re-authenticate. So it acts a lot like the KRB TGT account. If you've ever made the recommendation or been responsible for rotating that password, you're always told, wait 10 hours or 24 hours preferably. And the reason is it would stomp on all those sessions. So once we figured that out, that the blob is storing the current as well as the previous password to ensure that we wouldn't ticket stomp, we could decrypt everything. So here's the output of what the POC, once we've massaged the code a bit, is now we can decrypt the machine account passwords for both the CNO and the VCO. So if you ever mess with these passwords, they're all very, very long Unicode strings, which can be difficult for us to use. So the tool will just derive the RC4 and TLM hash of the CNO and the VCO, and now we can use those. So now we have the answer, like the high-level question of how Kerberos authentication works in the cluster is that every single node has access to the passwords for both of these roles at any given time. They're all in LSASS. When the cluster service starts up, it does a logon for those accounts, and it's ensuring that the credentials that it has are valid, and it can assume, in the event of a failover, it can go from the passive to the active node and handle that service. So what can we do as attackers if we control this? So we have access to service credentials at this point, right? We have the CNO and the VCO. There is a Kerberos extension called S for U to self, or service for user to self. We control the service, so we can use that extension to forge tickets for arbitrary users for services against ourselves. The benefit for this from the offensive side is there's really no protection against it. Protected users group doesn't apply. We can't say, like, mark the user account control to say cannot be delegated. So this is very, very beneficial for us. So let's kind of walk through an example of what that would look like once we've controlled that credential. OK, so we'll use getST. So we're going to perform that S for U to self. We're using the hash of the VCO account to generate that service ticket, and then we'll just export it and be able to use it for some other tools. So using another tool, we're going to connect to the cluster API. We're just impersonating a cluster admin, and now we'll start doing some enumeration. So we'll enum all the nodes in the cluster, find each endpoint that we have available to us, and then we'll check for the groups. And this is going to tell us what the cluster is, and then all of the roles that are installed on that cluster. From there, we can run the get group state command, and this will tell us who the active node is, who currently owns those roles. So we're looking for like who owns the file share role. We can simulate what we did in the beginning. Let's run the scheduled task command with silent, and we'll get a callback. From there, all we have to do is just move that resource to the next node, and then without doing anything with the ticket, without modifying it in any way, we can just run the same command, and now we have a callback on the other node. So we do that same step again. We're going to move the role from the node that we just set it on to the third node in the cluster, and then again, without modifying the ticket, without having to rerun that command at all, we'll just execute the task, and now we have executed a payload on all 3 nodes in the cluster with 1 ticket. So the result of that means that if we own the node, it doesn't matter how we got there, whatever control of the node, if we have admin rights to it, we therefore own the whole cluster. So all of the nodes in the cluster and all the roles that's hosting. But could it get worse? Can we own the domain from this point of view? To answer that question, we got to go back to the labbing. I purposely left this bit out so that we could talk about it here. So the CNO has some extra responsibilities in the cluster. It is the actual identity that is going to create and manage the VCO. So if you're going to have the CNO, your cluster in an organizational unit or OU that isn't in a default computers container, you're going to need to give the CNO certain permissions for that OU. The permission that is required is only create computer objects. This is the only permission that's required. If we go back and take a look at the lab guide that I was following, it is telling me to grant the CNO more than that. So generic right, create all child, and delete all child, which is way more than just create computer objects. It gets worse when you keep digging and you start looking for different ways of deploying these or troubleshooting things, because one thing that they don't mention in the documentation and very, very explicitly is that the CNO will also need the ability to modify DNS entries and so on and so forth. So to fix that, you'll see full control, generic all, generic write, create all computer, kind of grabbing create all child objects, just thrown around, which can lead to some problems. So the next few slides are going to be some attack graphs that start from a CNO compromise. So we have control over that virtual account. We have control over that identity. These are from different enterprise environments across different verticals. So here's an example of where we have control of a CNO. It was given generic right to an OU, and those permissions inherit down so far that we can go from a CNO to a DC sync. We can compromise the domain from there. Here's another example where the CNO is a member of a security group that has been given full control of the domain object, which means CNO to DC sync. Here's another example where the CNO is a member, has rights to a computer object that is a member of Exchange Trusted Subsystems, which I don't really have to talk about Exchange too much. It usually leads to a path to DC sync. And here's one of my favorite graphs is, so we have the control of a CNO, and we can follow a chain that gives us access to an identity that is synced to intra. So we can go from on-prem, jump up into intra, abuse some of the intra permissions, come back down on-prem, and then use that to compromise a DA. So from a virtual account that shouldn't exist, or that should exist but shouldn't be used, has a path to DA from a hybrid attack path. So what if the full control and the generic right or whatever doesn't lead to a path like this in any kind of way, and we just have those rights to an OU? It was always useful to have that because you could create computers, you could create users, but it didn't really lead to compromise of the domain. Like that wasn't a huge risk. Like, yeah, there were some issues, but it didn't lead to like the whole thing falling over. So that all changed earlier this year in May when Yuval Gordon from Akamai published this blog about BadSuccessor. Kind of broke the internet when this came out. So what happened here is, if you're not familiar, is he was investigating some of the services and the new features in Server 2025, in particular the DMSA, or the Delegated Managed Service account. And he found that if you were able to create this identity or create this object, you could abuse that object to impersonate privileged accounts and ultimately compromise the domain. So you needed the ability to create create the object, which we've seen is coming from those cluster objects. So he published this, and then like 5 minutes later, Logan Goins and some other developers, they published proof of concepts on abusing this. And that same day, I started seeing messages in like Bloodhound Slack and Discord channels where they were talking about, hey, what are these weird cluster accounts I'm seeing that have these permissions? Because people are trying to audit their environment to remove this. So they're looking for those permissions that we just talked about. So it's starting to get attention. People are starting to see what was going on. So let's back up from just focusing on the domain compromise, and remember what the clusters are intended to give high availability to. It's not just the domain, it's the services and resources that we're clustering. So earlier this week, Chris Thompson, so SQL, right? Our databases I said that was the most common, far and away the most common clustered service. So now it's under a bit of a microscope. Chris Thompson had published a blog where he had developed a Bloodhound collector that is focused entirely on MS SQL and analyzing the permissions that are associated with that. I'm not sure if you've ever tried to look at MS SQL permissions. It can be a mess, but this has made it easier, so it's going to be much more accessible to users to dig into this. What else? It's not just MS SQL. So ADFS has the option to have always-on availability groups. We can look at those. Earlier this year, there was a post by Max Keesley where he was investigating attack paths from the database side of things and compromising it through that route. Exchange uses a database availability group. So if you're still managing this on-prem, I'm sorry, especially recently with new CVs coming out. But the attack path we shared in the beginning actually started from a CNO in an Exchange DAG, or database availability group. So there's your proof that this is kind of a real world thing. Don't have any references there. Everyone knows how bad Exchange is. SCCM, or configuration manager, the brain of the entire thing. So all of your endpoint management, the brain of the entire thing lives in the database. So if that were to fall over, we lose access there. So you have high availability configs there, so clustered resources on the database. And SCCM's gotten a lot of attention recently as far as attack paths and domain compromise. And then the last one to share, because this one's interesting, is there's even Microsoft published documentation for clustering ADCS, or Active Directory Certificate Services. So 4 years ago, this was actually presented here at Black Hat by Will Schroeder and Lee Christensen, but with their talk certified pre-owned. At the time, they published it had 8 ESCs. I think we're approaching almost to 20 at this point. So, but they're actually clustering this service as well, which is interesting. So how common are clusters? I had a coworker kind of query all of the Bloodhound Enterprise tenants that we have, and we found that it was in 82% of the environments that we have access to. So 82% of the environments had at least one clustered role. The average number of unique clusters in each environment was 141. And then the top end of that in one environment had nearly 2,700 unique clusters. So that's a massive attack surface. So how do we go about fixing this? What do we do to kind of solve this problem? And it's the first step is really easy. Like, we only need that one permission in the OU that we're building the clusters in. So walk the permissions back, only create computer objects, So we're going to audit those cluster virtual accounts and see if they're giving those excessive permissions and try to fix that. There's that spin one more time, or that LDAP filter one more time if I've convinced you. I'll give you a sec to take a photo real quick. But on the detection side, we have, so that client access point, right? When we registered this, we assigned and reserved an IP address for that identity, for that object. We now know that it's also authenticating from, so it'll authenticate from here, but we now know that it's authenticating from every single node. So we have a list of expected logon locations. So if we see a authentication from any different source address, we have a reasonably high fidelity alert that something malicious is going on. Kind of keeping that same thought process going is we're like, okay, what can we monitor? Now that we understand that the cluster, these credentials live in registry and they're stored in this resource data key, we can monitor this. Only the cluster service and maybe its child processes like the resource control monitor will need to read the value of this entry. So we can create a SACL, which are always really strong for detecting malicious activity, and try to see if any other principal is trying to read the contents or value of that attribute. That was a duplicate slide, my bad. Okay, so key takeaways. Like what I want you to leave this conversation with. Number one is if you own the node, you own the cluster. It does not matter how you've gained control of it in any type of way. If you own one identity in there, you're going to own every single other identity associated with that cluster. And then lastly, second, cluster misconfigurations can lead to compromise. Purposely vague here because it's not just the domain, it's the compromise of those clustered services which are frequently tier 0, the things that would keep you up at night if they were to fall over. And the next piece is set it, but don't forget it. Remember, I started this whole thing off saying this has been around since 1997. Clustering is older than Active Directory itself, and we're creating these virtual identities, right? So these are AD accounts that aren't mapped to a host. Over time, the clustered resource, so the nodes themselves, are going to change. We're going to have operating system upgrades. It's going to go from bare metal to virtualization to maybe even up in the cloud. But these virtual accounts, these identities, aren't going to change. So the idea here is don't forget about them. Treat them the same as the active accounts and give them the same type of respect. But that's it. Real quick, I wanted to acknowledge some people that kind of contributed to the conversation, the biggest one being my wife, Riley. She is the reason that I'm here. And then a lot of the friends and the team over at SpecterOps. But that is it for the talk. Thank you. This is a QR code that will link you to the repository for the tool that I wrote to kind of interact with the RPC. It has a link to the proof of concept code for decrypting those credentials. And then the README has a high-level conversation of everything that we just talked about here. The detailed blog is on the way. I just have to finish writing it and get it through the QA process. But that's it. Thank you so much for attending. Are there any questions I can answer? I've got a couple minutes. Otherwise, I'll actually be heading to our booth to answer questions. But I do have some time. Are there any questions? Don't see them. So if there, oh, my bad. There is one right here. What's up? Yes, it'll be in the blog. So the question was, in case you didn't hear it, is do you have the Bloodhound queries that are relevant to find the clusters themselves? Yes. We also have to extend some of the, or work on some of the collection methods in Bloodhound to streamline that, and that's my responsibility. So that's in progress. Any other questions? I know it's lunch. You guys are probably all hungry, so doesn't look like it. Thanks again. I appreciate it. I know it's